Welcome to our segment about the physics of audio. Don't worry, this won't be a long and painful science lesson. However, an understanding of how sound works will help you, especially when you're editing and mixing your recordings. What is sound anyway? Sound is waves of air that radiate from vibrating objects around us, like our diva. When something vibrates, it moves back and forth and knocks the air molecules around it. All this jostling affects the air pressure of the surrounding molecules. It creates areas of higher pressure, called compression, and lower air pressure, called rarefaction. The waves move just like ripples around a rock that you've tossed into a pond. Our ears perceive this activity as sound. Here's what a sound wave looks like. Now let's talk about what makes a sound loud or soft. Let's go back to our pond again. When I throw a big rock, it falls with more energy, thus creating bigger ripples. If I were to throw a smaller rock, I would create smaller ripples. Well, sound works just like this. If something vibrates with more intensity, it creates a greater disturbance in the air around it. It creates a wave with a larger amplitude. Our ears perceive this as a louder sound. If I sing something quietly, I don't disturb the air molecules around my mouth as much, and thus the sound wave has smaller humps, less compression, less rarefaction of air. In technical terms, the volume of sound is related to the amplitude of the wave. Quieter sounds have lower amplitudes, and louder sounds have a greater amplitude. We measure amplitude with decibels of sound pressure level, or we call it dB. The human volume range ranges from 0 dB, which is silence, to about 130 decibels, which would be pretty painful. Now let's talk about pitch. While the amplitude of a sound wave, or its intensity, determines its volume, the pitch is determined by the speed of the vibration. If something vibrates more quickly, it creates more compressions and more rarefactions in any given time, and thus we hear it as a higher-pitched sound. If something vibrates more slowly, we hear it as a lower-pitched sound. The wave I have on the left is a slower wave than the wave I have on my right. Each cycle of compression and rarefaction is called a hertz. The frequency or pitch of sound is measured in hertz. The human ear can hear from about 20 to 20,000 hertz. The sensations of these frequencies are commonly referred to as pitch. A high pitch is a high frequency, and a low-pitch sound is a low frequency. Many musically trained people can in fact detect as small a difference as 2 hertz between sounds. 20 hertz, or 20 vibrations per second, is a really low sound. That's about an octave below the last note on your piano. The bottom A on the piano is about 32 hertz. 20,000 hertz would be about 2 octaves higher than the highest C on your piano. Human speech ranges from about 300 to 3,000 hertz, or about 3 octaves. The piano key C4, which we know as middle C, resonates at about 261 hertz. The C under that resonates at about half that frequency. As you can see, each of these Cs is separated by a 2-to-1 ratio. It's this 2-to-1 ratio that defines the interval of an octave. All intervals have a frequency ratio relationship between the 2 notes. The notes of a third resonate at a frequency of 5 to 4. Let's take a look at C and E on my piano. And it's not just this third, it's all thirds that share this relationship of 5 over 4. Same thing with a fourth. Let's take a look at F above middle C and middle C. They create a relationship of 4 over 3, and all fourths will resonate at this relationship. And this concludes our basic introduction to audio physics.